All right, so today's topic is dark matter. Okay, so it's my favorite research topic. The goal of today's talk first is to tell you about what we know about dark matter, right? What do we mean when we say these two words, dark matter? I'm going to tell you then what we don't know about dark matter. Okay, we know surprisingly a lot about dark matter, but of course there are things that we don't know. That's why we are doing the research. At the end, I'll give you some brief overview about the current trend and the status of several hot dark matter research areas. So first, what is dark matter? Okay, I would call it the dark matter phenomenon. It all begins back into the 30s. Okay, so this guy is Sawicki. So he was studying a group of clusters called the Coma galaxy cluster. So a galaxy cluster is a gravitational bound object, okay, consists of galaxies. Okay, so imagine a galaxy, right, is a collection of stars. Then a galaxy clusters is a collection of galaxies. So what Sawicki did and his innovation was to apply the Vivio theorem to this collection of gravitationally bound objects. And Vivio theorem told us that 2 times the kinetic energy is equal to potential energy, right? So what is kinetic energy for these galaxies? So basically, Sawicki can measure how fast these galaxies move in the Coma cluster. So from the velocities, we know the kinetic energy, okay? The Vivio theorem should apply, okay, if we also compute the potential energy of these objects, okay? So the gravitational potential energy of these objects. And you know, the gravitational potential energy depends on the gravitational mass of these objects. Okay, so that's the logic of his analysis, right? So applying Vivio theorem, okay, you should figure out the kinetic energy and the potential energy of these objects, and they should agree. Surprisingly, back then, it was found that if you just did this exercise, all these galaxies are moving way faster than his initial estimates. Okay, so what happened was that if you just count the number of galaxies in this object and use that to compute your gravitational potential energy, you significantly underestimate how fast they should move. Okay, so the conclusion was that, all right, there should be some missing gravitational contribution, okay, from not galaxies in the Coma cluster. Okay. So this is in the 30s, and people will say, oh, hey, this is pretty cool. That probably means that we did something wrong. All right. People suggest many alternative explanations to this. Maybe there's some hidden non-luminous gas inside. Okay, maybe there's black holes, who knows? But people start to realize just by optical observations, it's not enough to measure all the matter, okay, in a galaxy cluster. So from the 30s to 70s, okay, this problem continues. And the notion of dark matter was slowly developed back then. But it really only became a truly serious problem in astrophysics back in the 70s, when the study of rotation curve made possible, okay, from giant advancements in astrophysical observations. So this kind of work was pioneered or led by Vera Rubin. Okay, one of the first examples she did was to look at the Andromeda galaxy. Okay, if you don't know, Andromeda galaxy is one of the rare galaxies you can see by your naked eye in a clear sky. So you should try to find it. So what people did back then was to measure how fast the Andromeda galaxy was rotating. So inside this galaxy, all these bright lights are stars, and they're rotating around the center. So if you just measured each point in here, because it's rotating, so they're either moving towards you or away from you. So you should be able to use blue shift or red shift to measure the velocity. Then you can construct a rotation curve, meaning at each point from the center, how fast this galaxy is rotating. Okay, so that's the meaning of a rotation curve. And simply from Newtonian mechanics, you know how fast these stars should be rotating given the gravitational force, given the gravitational force produced by the galaxy itself, meaning the mass of the galaxy itself. So again, we have a measurement that's using the velocities of the object, we can try to measure the gravitational mass. And so this was what was done sort of back then. Now we of course have much more precise data, and I'm telling you the current status of the M31 model, the Andromeda mass model. These points are the rotation curve, okay? There are some that's inside here that's omitted. But basically, what was discovered is that using only visible matter, okay, nowadays, in addition to stars, in structures like bulge and this, we also have measurements on gas. All these visible matters cannot explain how fast Andromeda is moving, okay? If you look at these curves in here, they can only explain maybe up to 100 kilometers per second, but the data is around 200. Okay. So again, we have a situation that is visible matters cannot explain how fast they're moving, meaning that they cannot explain the full gravitational potential. Okay, so this is when people truly realize, okay, that the dark matter phenomenon is a serious problem. So you can solve this by fitting a hypothetical component, okay, so in this case called dark matter halo, and try to explain the missing matter parts. Okay, so you do this, you fit it, and in addition to telling you that dark matter exists, this actually also tells you how dark matter are distributed inside the galaxy. Okay, this is a very significant advancement. Okay, not only we are missing matter, we are also missing a type of matter that are distributed differently compared to normal matter. Okay, so this is already there's something we can already learn here. We know that normal matter, right, things you know, hydrogen gas, okay, electron, things like this, in our galaxy, they have already been collapsed due to radiative interactions between themselves, okay, through their evolution. That's why they can form stars and they are shining in the center of our galaxies. But dark matter cannot participate in these kind of interactions. Otherwise, they would also they are expected to also collapse into compact objects in the center. But from these kind of studies, we know that dark matter are much more sparsely distributed. Okay, so dark matter cannot have EM-like force, simply from the rotation curve studies. So this was done in the 70s, and that's when dark matter become a truly important problem in astrophysics. So this is a bit of sociology, showing you the amount of dark matters per year, okay, from the 70s when they start to track these papers. And you can see there is a kind of exponential growth on the number of papers per year, kind of like our COVID case in Hong Kong. And this is telling you that the dark matter problem is becoming more and more important to the community. Okay? And I will tell you more why later. All right, so we've discussed galaxy clusters and galaxies themselves, that we know that now that they are missing matter, okay, and we know that these kind of matter do not behave like normal matter. The next important clue that we get about dark matter is from the Bullet cluster. So what is it? It can be understood if we just look at this video. Okay. So the bullet cluster consists of a normal galaxy cluster, okay? And then there's another galaxy cluster that actually pass through it. The bullet is called bullets because this smaller galaxy cluster acts like a bullet and penetrates the original cluster, okay? This simple phenomena actually tells us a lot because there are three distinctive components in this object, okay? First are the galaxies. So these bright objects are the galaxies. If you look at the simulation, you will see that the galaxies, they just flow around and they basically do not change when the small galaxy cluster passes through. That's because over this space, the galaxies themselves are tiny. So the probability of them interacting when another galaxy cluster passes through is very small. So galaxies, they do not quite move. But you see these red things, okay? These are actually traced by X-rays. These are hot gas traced using X-rays, okay? And you see the X-rays, the X-ray traced hot gas matter, they actually interact when the small galaxy passes through. This is because these ionized gas exhibit very strong electromagnetic interactions, okay? They are partially charged. So you see there's even a shock front developed after passing through. So this tells you what do you expect if matter interact with EM force, okay? So we have galaxies, the point objects that you see, and you also have the hot gas component. Then there's the blue component, okay? These are actually invisible components, but we know they contribute to most of the mass of the galaxies using gravitational lensing, okay? So gravitational lensing is basically, if there's a lot of mass in here, they can lens, just like a normal glass lens, they can lens the light from bright objects behind, they can bend it. So from reconstructing how the background objects are lensed by these mass, we can find out how much mass in here. So the blue part is telling us most of the mass are actually contained in here, okay? So they follow the galaxies themselves, okay, but not the X-ray mass. Then this comes to the combining all these things. We know that the gravitational mass, they basically do not interact with each other. Otherwise, they would follow the X-ray mass, okay? And the galaxy themselves, you can just count all of them. They cannot explain the total mass inside this the galaxy cluster, okay? So what we can learn here is that these dark matter, right, that contributes most to the mass in the blue region, they cannot strongly self-interact, okay? Not only they cannot interact with the strength of a EM force, they cannot interact even with, they cannot interact with any kind of force as strong as just like a normal matter collision. Okay? And obviously, this is another evidence that there's a missing dark matter present in here. Okay? So these are all individual object studies, right? Bullet cluster, and then rotation curves, and then coma cluster. In the late 80s, 90s, and the 2000-ish, the precision cosmology studies has become very, very powerful. Okay, basically is that we now have a much better understanding how the universe evolved from way early in time. Okay, we know that the universe was expanding. Okay, so it's expanding in the future. That means in the past it must be contracted, right? And that means at some point in the universe, it was in a very hot and dense state, okay? So we now have stars, okay? If you rewind back in time, that means it must be some kind of gas that has not been collapsed. And then if you rewind back even further, when the gas is very dense, that means they're very hot, that means they're in an ionized state. And if you keep going into even earlier in the universe was made with 3 quarks, 3 electrons, it's like a soup of fundamental particles. Okay. So what's important about this picture is that general relativity told us how fast the universe should expand given the matter and energy density, right, in the universe. So I will not go into details in this, but this is what you should remember. What's in the universe at that point determined how the universe is expanding. Okay. So there are 2 very important studies. Okay. One is called Big Bang nuclear synthesis. At very, very early in the universe, we only have 3 protons and neutrons. Okay, so there's no heavy elements, no helium, no gold whatsoever. But as the universe continues to expand and cool, eventually some of the elements can be formed and be left over. This is a picture, okay, as a function of time, so early in time and late in time. And these lines are showing you the abundance of different elements. Okay, so this is helium, and then deuterium, helium-3, and then some light elements like beryllium and lithium. So at the beginning, we only have hydrogen, so protons and neutrons. But after some time, you start to form these elements, and then they are left over till today. Okay. So this process is a competition between nuclear interactions that form these elements, and also the expansion of the universe. Because if the universe expands very, very fast, the formation reaction of these things will stop. If the universe expands very slowly, okay, these reactions can continue and form a different elemental abundance. So BBN actually tells us how much the universe contains, how much normal matter the universe contains, okay? Because obviously the abundance depends on the reactants, which are the normal hydrogens and neutrons. But BBN also tells us how fast at this point in time the universe was expanding, okay? And remember, this tells us the expansion, how fast it's expanding depends on the total matter density in the universe, okay? So the other precision cosmology tool that we have is the cosmic microwave background anisotropy. This is basically a picture of the universe, okay, when it was transitioning from a plasma state to a neutral state. Okay, so basically, when the universe was made with ionized protons, okay, ionized hydrogen, so just protons, as well as photon. Because it's continually being expanded, it's continually being cooled, they will eventually form neutral hydrogen. And this is a picture of the time at that moment. It's not completely smooth, it's inhomogeneous at the 10 to the minus 5 level. And so these red spots means at that point, it was hotter. And if you let these matter distributions continue to evolve, eventually they form different galaxies and then clusters of galaxies. Okay, this is what the universe looks like after billions of years of evolution. Okay, so the CMB also tells us that the matter, dark matter, in fact, most of the matter must be non-relativistic. Otherwise, they cannot collapse into and form galaxies just like this. So to summarize the precision cosmology studies, okay, I don't have time to do this. We collectively learned something, is that the universe itself is made with 3 very distinctive components. Okay, there's more if we look into what's in here, but basically there are 3 types. There's dark energy that controls the late time accelerated expansion of the universe, which we will discuss here. Then there's matter component, okay, and inside the matter component, most of them is a component that's called dark matter. And the matter that we know, protons, neutrons, electrons, things like that, only made up with the 5% of the total energy budget of the universe. Okay. So in fact, most of the matter in the universe are not the ones that we know. Okay. Most of them is contained in a component that we have no idea what it is. Okay. So now I want to clarify what we mean by the dark matter, or I would say the dark matter phenomenon. If you notice all the discussions I've made, okay, we infer the existence of dark matter, use basically all of them involve this logic. Okay, we use gravity, right, gravitational matter. Okay, either it's how fast galaxies is rotating, or either how the universe is expanding. All of them are gravity measurements. Okay, we compare with observations that we made, okay, for normal matter, right? So BBM basically we measure normal matter using nuclear interactions, or galaxies, right? We just look at how many stars there are. All of these are normal matter measurements using forces that we know, right? Whether it's EM force or nuclear force. And dark matter comes up when these two measurements does not match, okay? So really, there are two possibilities on what goes wrong in this inequality, right? Because we use gravity, obviously one possibility is that gravity might be wrong, right? Our theory of gravity, either it's Newtonian in the galaxy scale, or general relativity in the cosmological scale is wrong. So in fact, a solution to the dark matter phenomena is not introducing a new type of matter. Okay? You can actually try to solve this problem by modifying gravity. And I can tell you that the advantage of this approach is that it's easier to describe what you see in the galaxy scales, because modifying Newtonian gravity, for example, the usual Newtonian law like this, it's not that difficult. But modifying gravities in a cosmological scale and still make your theory consistent with BBN and CMB is very difficult, because general relativity is more difficult to modify and still make it self-consistent. So if you don't modify gravity, that means you have to modify the right-hand side parts. Okay, so our observational normal matter cannot be all the matter is there. So that's basically what we discussed for the rest of today. Okay, we will modify the matter model, meaning the standard model of particle physics. Okay, it's not complete. There should be at least one new type of matter that explains the missing matter. Okay, so just adding these new kind of matter, cosmologically, it makes things easy, right? It's easy to introduce a non-interacting type of matter and to explain BBN and cosmic microwave background. But actually, in the galaxy scale, okay, to include these kind of matter and to explain everything in the galaxy scale, it itself is a challenge. Okay, so MC actually did this kind of research, so maybe he told you what he did last week. Okay, but this is a very big topic, but it's not directly related to what we will discuss today, meaning identification of dark matter. So I will not go deeper into this. Oh, by the way, so all the topics I discussed today, I can only give you an overview. Okay, so if you have any questions or if you want to know more about specific parts of any of the things I discussed today, feel free to let me know afterwards or ask me in the questions. All right, so there are two ways you can modify the dark matter. You can resolve the dark matter phenomenon, right? I will, for the rest of today, we will only look at modifying the matter parts. Okay, so to do that, let's have a quick review of what the standard model of particle physics is. Okay, it's the most successful, okay, particle physics model we have. Explains all our matter observations and all of the interactions. Okay, so it has quarks, leptons, the force carriers, okay, as well as a Higgs. So before we required that we need to introduce a new matter to explain dark matter. Okay, first, obviously, we should look into this to see if we have dark matter candidates. Actually, that was what people did first, okay, when they noticed there are missing matter in the COMAS cluster, because it is possible to explain the missing matters with rocks, dust, okay, or maybe even dim stars that you simply do not see. Okay, but these are ruled out by BBN and CMB. Okay, because BBN tells us that they cannot participate in nuclear fusion, and all these things, if you look at them in the early universe, will do that. Okay, so that means looking at this table, first we should immediately rule out all the unstable particles. Okay, so everything in the right-hand side part is ruled out. So protons and neutrons cannot do that because they are not rocks, because they are either they are contained in the rocks and dust, right? Really, the only possibility that the standard model can have a dark matter candidate is neutrinos, and that was what people was thinking in the 80s and 70s. But nowadays we know that neutrinos cannot, because we have a much better idea on the mass of the neutrinos. They simply do not make up enough amount of dark matter in the universe. So these are normal neutrinos. Later, I will introduce a new kind of neutrinos, but you need to remember it's not the same neutrinos that you typically see in the standard model particle charts. Okay. So, okay, what we really know about dark matter. Okay, so here's is basically a summary of the fact sheets that what we know. We know that it's cold, okay, meaning it must not move very fast in the early universe. Okay, this typically means that it cannot be very, very light, because otherwise it cannot collapse and form galaxies. It must be cosmologically stable. Okay, if it decays, then it will disappear after some time, right? But dark matter is there from BBN to galaxy formation, basically now. So it must be cosmologically stable, or its decay time is much longer than the age of the universe. We know how much there it is actually. Okay, 25% of all energy budget in the universe. And remember, this is the energy density budget. It's in dark matter, roughly. Okay. So we know this in the global cosmological scale. We actually also know how much dark matter there is, okay, locally at the position of the sun. Because we can model the Milky Way rotation curve, just like basically what we did, okay, for M31. So in this model, okay, for example, you can pick out exactly how much dark matter density there is, okay, as a function of distance from the galaxy center. So just construct this model for Milky Way, and you know exactly how much dark matter there is in the position of the sun. So we have a number for that. We know roughly, locally, the dark matter density is 0.3 GeV. 1 GeV is roughly 1 mass of a proton per centimeter cube. Okay, so if you imagine dark matter has mass of 1 GeV, there's one of them per centimeter cube. We also roughly know how fast it moves, okay, because you need to model, explain the Milky Way rotation curves, about 200 kilometers per second. So if dark matter, right, has mass 1 GeV, okay, they are constantly passing through you with speed that's more than 200 kilometers per second. So we know this, and we also know that it cannot have very strong self interactions from bullet cluster, and there's no signs of detection of it having electroweak force or strong force. Okay, so no standard model, no known detections of standard model interactions. Okay, and unfortunately, this is the list. Okay, that's basically what we know about dark matter. Everything else, we don't know what dark matter is. Right? We don't know whether it's a boson, whether it's a fermion, and we don't know its mass, and we don't know what kind of interactions it has. Okay, so that's the goal of dark matter research. We want to identify dark matter. Okay, so this is showing you the possibility of the what the dark matter mass could be. Okay, if you look at the scales, okay, you should be frightened. It ranges from small CeV. So if I remember, this is 10 to the minus 18, up to 30 solar mass. Okay, so it's 10 to the power 30 something. Okay, GeV. Sorry, 10 to the power something gram. So if you, it's 10 to the power almost 60 GeV. So it's a huge horizontal range, okay, of possibilities. We don't know what the mass of dark matter. That's not entirely true. Okay, we know we have hard boundaries. Okay, so if dark matter is a boson, okay, we know that it cannot be much smaller than 10 to the minus 22 eV. Okay, otherwise its quantum wavelengths would be larger than a small galaxy. Okay, the situation is better if dark matter is a fermion. Okay, because of Fermi-Dirac statistics, you cannot cram fermions into a finite physical and velocity space. Okay, so we know that if dark matter is a fermion, its mass must be larger than 1 keV because of the finite phase space. Okay, and we know that it cannot be it cannot be larger than solar mass, roughly. Okay, otherwise it would, as it pass through stars, okay, it would lens the light of stars. So we do have some hard boundaries, but other than that, we don't really know what dark matter, what the mass of dark matter is. Okay, so here it's a reality check. Okay, sometimes people ask me, and sometimes I ask this myself. Maybe we will never know what dark matter is. Okay, so it's important to realize that this is actually possible. Okay, there are models of dark matter that would imply dark matter will never be identified, meaning that they basically only have gravitational interaction. There's no way of detection. Okay, but this, even though it's possible, okay, the dark matter problem is too important to give up. Okay, because it likely connects to other very important problems in particle physics. Okay, I will discuss more later. Another point is that through our quest to identify dark matter, there are actually many things that we learned on the way. Okay, so it's not like every negative search of dark matter is useless. There are actually many things that has been discovered or that allow us to actually find through this journey. So, okay, let me start telling you how we try to identify dark matter. There are two types of people, okay, that research dark matter. One is model builders. Okay, so you are a particle theorist. Okay, you try to make up a model of what dark matter could be. Okay. The other type of dark matter researchers are dark matter searchers. Okay, you try to use whatever observation or you try to propose a methods to identify dark matter. Okay, so I'm in this class, but I will tell you what the model builders have been doing. Okay, this is more or less a landscape of popular dark matter possibilities. Okay, just basically there are too many possibilities that dark matter can be. Okay, so I will not go into this. It's easier to look at this chart. This is the energy scales in terms of the physics that we know. Okay, so the x-axis is energy. We know a proton mass is 1 GeV. It's in here. So electron is here, neutrino is way down here. So for the past 50 years in the particle physics research, we have been pushing to increase energy. Right? We build more and more powerful colliders, and we try to discover new particles. And the fact is that we have discovered many particles along as we push along this axis up to 1 TeV. Right? So we discovered new types of quarks. We discovered force carriers like Ws and Cs, and we have discovered Higgs just recently. Okay, but we also know that this energy scale is very limited. Okay, right now in XC we hit TeV, so around here. But this is still a very short distance compared to what we expect the full energy range of physics. For example, we expect gravity and quantum mechanics unify in the Planck scale. Okay, so it's already more than 10 orders of magnitude higher. Okay. We know that our three fundamental forces, EM and weak and strong force, we expect them to unify in this energy scale, so just below the quantum gravity scale. And this alone is also very, very far away from where we are now. Okay. So since we've discovered so many new particles and so many new physics in here, okay, it is very possible that there are also many new physics in this energy range. Okay. So this is a common belief that our standard model, even though it's very successful, it's only a low energy approximation of a full theory. Either it's a quantum gravity theory or a grand unification theory, or whatever theory that's in this energy scale. Our standard model is only an approximation. Okay. So there are many open problems that in the particle physics right now that standard model cannot be solved. Here is just a few of them. So one of them is the so-called hierarchy problem. Basically, it asks, why is the Higgs boson so light? Why is it only 200 GeV? Because all the potential new particles in this energy range, okay, should add corrections to the Higgs mass. Okay, should affect the mass of the Higgs that you measure. So if you have a correction from 10 to the 12 GeV, why is your Higgs not 10 to the 12 GeV? So this is the hierarchy problem. And the potential solution is that maybe we have a supersymmetry theory. Okay, supersymmetry theory that states that every pair of the particles in the universe should have its counterpart. Right? If it's a boson, it should have a fermion counterpart. If it's a fermion, it should have a bosonic counterpart. And with this, if supersymmetry exists, okay, all the mass corrections to the Higgs will be canceled out. Okay, and that's then Higgs could be naturally light. So this supersymmetry is not the only idea to solve the hierarchy problem. Okay, there are many other ideas. For example, extra dimension, blah blah blah. Okay, so this is one of the most important problems in particle physics. Okay, another problem is the strong CP problem. Basically, it asks why neutron electric dipole moment is so small. In the standard model, there's no physics that forbids the neutron electric dipole moment. Okay, but it's small. So why is this number that we expect to be order 1 to be incredibly small? Okay, and usually these kind of things happens in physics for a reason. Okay, and solution is a new kind of particle called axions. Okay, so these are open questions in the universe. I will not go through all of them, but what I want you to take away is in a lot of these, in a lot of the solutions to these problems, there's a dark matter candidate. Okay, So a type of new matter that is not very strongly interacting with the rest of the matter is actually very common predictions if you want to modify the standard model. Okay, so that's why we have so many dark matter candidates in this picture. Okay, so this is from the perspective of a model builder. Okay, you want to solve these problems, and when you try to do that, okay, you produce a dark matter candidate. There's another perspective, and that's the astrophysical problems. Okay, in many astrophysical observations, usually you find anomalies, things that you cannot explain. Okay, and sometimes, okay, these anomalies can be explained by very popular models, very popular dark matter models. Okay, so this triggered a lot of times a lot of excitement on whether these could be dark matter discoveries. Okay, for example, people have discovered gamma ray access towards our galactic center, where we expect there are a lot of dark matter, and people have found lines, okay, in the X-ray energy band where it's very difficult to explain. Okay, and also for the cosmological, in the cosmological scale, okay, the lambda CDM, in the galaxy formation scale, okay, it's very difficult to make simulation to agree with observations. Okay, and these are maybe all of these contains hints on what dark matter could be. Okay, so this is the astrophysical perspective. Okay, but basically, okay, the dark matter strategies a lot of times depends on these two perspectives. Okay, so the model builders, we have dark matter candidates that tells us how dark matters might interact. Okay, alternatively, there are anomalies or there are unresolved problems in astrophysics. Okay, and these two factors both affect the dark matter strategy. Okay, so in the remaining time, so I'll quickly go over some popular dark matter strategies. Okay. So one of the most popular dark matter candidates is called weakly interacting massive particles, or just WIMPs. Okay. It's a very popular candidate because it's a generic byproduct of many theories like supersymmetry or extra dimension. Okay. What it does is that it participates in a 2-to-2 reactions that just like this. Okay. So two legs are standard model particles, and two of the legs are dark matter themselves. So if you look at this direction, okay, up, that means you can merge two standard model particles and form two dark matter particles. Okay, this is in fact how WIMPs could be produced in the early universe. Okay, when there's a lot of standard model interactions, and of course, this diagram can be looked downwards. That means if you have a collection of dark matter, they can self-annihilate and become standard model particles. So if you detect these standard model particles, it could tell you what the dark matter mass and the interaction could be. Okay, so that's why if you look down, if you go down, this route is called the indirect detection. So one very nice thing about WIMP is that its production mechanism naturally predicts a interaction strength scale, okay, about 10 to the minus 26 centimeter cube per second for the cross section, okay, to explain the observed dark matter abundance. Okay, so this gives us a scale that we can aim for, okay, to test this generic WIMPs. So WIMPs allow us to use indirect detection. Okay, that's not the only way. If you look at this diagram from sideways, okay, that means in dark matter and standard model states, they can interact. Okay, so dark matter can interact standard model particle and becoming another dark matter and standard model particle. Okay, if these two standard model states are the same, that means this is a elastic interaction. Okay, so that means if you have a materials in here with a dark matter come in, okay, and it will hit something in your material. So you can do this, and it's called direct detection. And finally, okay, another way to look at this diagram is to look into the up direction. This was how dark matter was produced in the early universe. That means we can recreate this condition in collider. Right? Just smash two standard model particles together. You could produce dark matter in your collider. Okay, so this three directions forms the three axes of strategies to search for WIMPs. Okay, I'll go through them quickly and sort of overview their situation. So as I said, direct detection, you build a detector and you wait for dark matter to come in and hits one of them, right? So it will leave some recoil energy. If you can detect this signature, you detected dark matter. All right, it sounds very simple, but reality, okay, you have to take care of two important factors. So one of them is that you want to shield your detector, okay, from outside disturbance, okay, from high energy particles from space, just from normal standard model physics, and also other human behaviors. Okay, so to do a good direct detection search, you want to go very deep underground. Okay, so this is showing basically some of the sites that host direct detection experiments, and they have to go more than 1 kilometer underground. Okay. Another factors you need, because the amount of interaction is expected small, because the interactions are small, you want a large detector. Okay, so you want a detection technology that can scale up your detection. And this is the direction, the status of direct detection experiment. Okay, so you see many lines here. This is a plot for cross-section, the dark matter and normal matter, okay, nucleon cross-section, interaction cross-section, as a function of dark matter mass. Okay? We don't know what dark matter mass is, so we have to make this plot as a function of dark matter mass. So each line here represents a result. Okay, solid lines are experiments that has already been done. Okay, and dashed lines are future experiments. So lines means that they have not seen anything. Okay, so it means they rule out the parameters space above. Okay, so that's why the dashed lines you want to push as low as possible. Okay, you want to go to lower cross sections. Okay. So, and you see there are closed loops here. So these are some of the claims. Okay, some of the claims, but you see all of them falls below solid lines. Okay, so these claims have not been substantiated, okay, unfortunately. And I want you to look at this vertical scale. So these are cross sections around 10 to the minus 40, okay, 4. Okay, these are 20 orders of magnitude below typical electromagnetic interaction strength. Okay? So that means that tells us that dark matter interaction with normal matter is indeed very weak. Otherwise, we should have seen something. Okay, so that's the status of direct detection. Okay, there are many proposed experiments to go as down as possible. But there are challenges for direct detections. Okay, one is that it's very difficult to go to smaller dark matter mass. Okay, you see all these lines go up in here. This is because, hey, although we don't know what dark matter mass is, we know its velocity in the Milky Way. It's only 200 kilometers per second. So if the dark matter mass is small, okay, that means at each hit, the energy deposited is smaller, right? And a experiment always have an energy threshold, right, where below it cannot sense anything. Okay? So that's why it's very difficult to detect smaller dark matter mass. Another challenge it has is that, okay, you see there is a giant solid line here that's shaded. This is the so-called neutrino floor. Because at some point, when the dark matter experiments build up to a certain scale, they can start to see neutrinos interact with their detection materials elastically. Okay, so these are called coherent neutrino scatterings. Okay? And these neutrinos are just normal neutrinos from the sun or from the atmosphere just flying around. But if they have detected these interactions, it will just look exactly like a dark matter interaction. Okay, so there's no way for them to tell apart these neutrino interactions versus a dark matter interaction. That's why it's called a neutrino flaw, because these parameter space will be very, very difficult to probe because you will expect to see neutrinos in here. Okay. So in the field of direct detections, a very major component right now is to find new ideas to bypass these challenges. Okay. For example, how to go beyond the neutrino flow. Okay, you need to find something that's different from neutrino interactions. One way to do it is to use directional detection. Okay? If your detection idea can have some information about where the particle is flying from. That's because the solar system is actually rotating around the galactic center with about 200 kilometers per second. Okay, so that means when the Earth is rotating like this, okay, we are actually going towards a dark matter wing. Okay, and when the Earth is at this position, we are going sort of against a dark matter, following the dark matter wing. Okay, so there will be some yearly time dependent signatures like this that allows us to differentiate from neutrinos. Another important axis of research is to come up with new detection technologies or ideas that allow us to detect smaller dark matter mass. Okay, so for example, it has been proposed something like liquid helium. Okay, so as a detection material. Basically, in the past few years, people are trying to capitalize okay, the significant advancements in condensed matter physics with all those fancy materials to come up with a next generation dark matter detection technology. Okay. So I know maybe some of you works in the condensed matter area, and if you have an idea, please let me know. Okay. All right. Another idea is that to detect light dark matter, for example, is to consider the acceleration of dark matter in space. As I told you, it's difficult to go below this line because dark matter do not have enough kinetic energy. Right? But maybe some dark matters are accelerated in space. One idea is that a cosmic rays, a fast-moving normal standard model particles, can hit a slow-moving dark matter. Right? Then the dark matters will gain some energy and move faster. Okay. Now, if this dark matter enters the detector, they will leave a much higher energy signature. So your detector will see it. Okay. So this idea allows, okay, in the past few years, probing that's considering these kind of reactions to probe parameter space in this region. Okay. So only in the past few years, the light dark matter sensitivity has been improved by more than 5 orders of magnitude. This is very exciting, right? Direct detection has existed for more than 20 years, okay? But it only is in the past few years, people have come up with new ideas. That's easy to do ideas to expand the detection of light dark matter, okay? So new ideas in this case is much more important, okay, much easier comparing to developing new experiments. Okay, so unfortunately, I realize I don't have time to go through some of these, but I think we can stop in the direct detection parts. Okay, so I just want to summarize. Okay. So some people doubt the existence of dark matter. Okay, it depends on what you ask. Okay, there's no question that gravitational observation, okay, and non-gravitational observation in many different scenarios are inconsistent. Okay, this to me means that there's no question that dark matter exists. Okay, it's just that we don't know whether you have to modify gravity or modify standard model of particle physics. But I can tell you that modifying standard model particle physics is much more well motivated because there are many known problems in the standard model of particle physics. Okay. So the dark matter identification, okay, of course, it's very difficult. Okay. The problem is that it's not that we have no good candidates. The problem is that we have too many good candidates. Okay. And we need to basically to advance the dark matter search aspects. Okay. The things I think we need the most are innovative new ideas. Okay, that allows us to push dark matter sensitivity. Okay, new ideas about new ways to detect dark matter, where it's direct detection, or the unfortunately things that I did not have time to cover, the indirect detection aspect. Okay. And importantly, to be more sensitive, to do more sensitive dark matter searches, it is important to understand the competing astrophysics process. Okay. So yeah, that's what I want to say today. Any questions?
Yes, Kenny, a question over here.
Yeah.
Okay, so about the bullet cluster collision, even though I've seen it sometimes now, but this is the first time. This collision doesn't happen on human timescale or observable timescale, right? We are not observing this event real time.
No. Yeah.
Then how do we know it is a collision, not some other relic of some other interaction?
Very good. So it has already happened, right? When we observe it. Okay. But all the physics here are time reversible, right? It's just gravity. So you can rewind in time and you would realize that the motion of these things are moving right, in this direction. Okay. The second clue is that there is a very sharp edge in the X-ray gas in here. Okay. This is formed when a small cluster of gas that penetrates a larger clump of gas and form a sharp front. Okay. So this is why it's a significant hint that they have collided.
Okay, thanks.
Yeah.
I also have a question. So we have already observed the neutrino coherent scattering, right?
Yes.
But is it possible we actually have already detected the dark matter?
Okay, so yes, we have detected neutrino coherent scattering. Okay, but these detections were not performed in a dark matter detector. Okay? So people actually built a detector next to a very intense neutrino beam, okay, near a neutron spallation source. Okay? And we know there's a lot of neutrons happening there. You don't want to put a dark matter in those environments, right? Because you want to reduce the neutrino background as much as possible. Yeah. So in a dark matter detector, I think there's one candidate event that looks like a neutrino. Okay. But it's hard to tell because there's only one event. Yeah,
but if
it's by the xenon, it's by the xenon detector. Yeah.
Yeah, but if we actually have a detector to detect the yellow regions, then why can we not just to subtract the neutrino background?
Okay, very good question. So for example, right, if you have a detector that have detected this neutrino, let's say you have detected 100 of them. Okay.
Okay.
If you have detected 100, that means your expected number of events could be something like 80 to 120. Okay. So that means there is about 40 events of room you can hide your dark matter signal into it. Right. So it's very, that means it's very difficult to infer if there's any dark matter signals inside. So what you said is true only if you can detect many neutrino events. Right. But that is very difficult.
Okay, yeah.
Yeah, because
but I mean if the okay, I see.
Yeah, because it depends on the error bar.
Yeah, right.
And Kenny, I want to know more. So unfortunately, you don't have time, but I think when you encounter, when you are introducing the standard model, you said something about the search of an extra neutrino. So I don't know whether you're referring to maybe zero neutrino, but can you tell maybe a little bit more about it?
Yes. So one of the open problems in standard model is that we don't understand why neutrino mass is so small. Okay, so actually in the standard model, neutrinos are massless. Okay, it's very easy to give neutrino a mass, right? Just like the rest of the fermions, they get a mass from Higgs mechanism. Okay, you add the right-handed neutrinos to the standard model, then you have a Dirac mass term. But then why is neutrino mass so small? Okay, so why is the your Yukawa coupling so small? So another possibility is that neutrinos, maybe they are Majorana, then they can have Majorana mass terms. Okay, so neutrinos can have both Dirac and Majorana mass terms. Okay, or both additions will be beyond the standard model. Okay, but this regardless, if right-handed neutrinos exist, okay, so if there is a Dirac mass term, right-handed neutrinos are very good dark matter candidates. Okay, so they're also called stereo neutrinos. That's the thing that you're referring to. Okay. So depending on the specific solution to explain why neutrinos has mass and why its mass is so small, okay, the corresponding stereo neutrino could be a dark matter candidate. Does that answer your question?
Yes, thank you.
Yeah.
And since the dark matter has mass, does it mean the dark matter need to couple with Higgs boson?
Higgs boson is not the only way you can get a mass, right? You can always get a mass from some other mechanism. So there's no guarantee.
Okay.
Yeah, and you could have more than one Higgs-like bosons that give mass to particles.
Yeah, right.
Yeah.
So I have a more general question about the astrophysical observation about the dark matter. So at first we have this rotational curve.
Yes.
And I think in recent years, we also have some gravitational lensing of the EM signal and try to also study the distribution of this dark matter. So I wonder how consistent these two different kind of astrophysical observation.
Yeah, very good question. So you see, to model the rotation curve, you need to fit a dark matter halo like this in here, right? At the moment, okay, both gravitational lensing method and rotational curve methods can be used to infer what the distribution of dark matter you need, right? But at the moment, gravitational lensing method are not as strong or as restrictive as the rotational curve method. The results are consistent with each other.
I see.
Yeah, yeah. So I think only a few years ago, they claimed that okay, they can finally get a preference that's this halo shape is a good fit. Okay? So before they say, oh, we need extra matter. Now they say, okay, we need some kind of shape that agrees with these shapes.
That's interesting.
Yeah.
And also I think there is a recent paper that is about a new observation that dark matter can not be exist in some galaxy.
Yeah, so very good. So that's the difficult in parts of astrophysics. Okay, galaxy physics in dark matter model is difficult because galaxy physics are extremely nonlinear, right? What do you mean by nonlinear? Early universe, the inhomogeneity scale is very small. Okay, so any perturbations are small. Okay, so these are, you can do this with linear perturbation theory. But these inhomogeneities, right, will grow as a function of time because gravity, denser regions will become denser simply of gravity. So they will form galaxies. Okay, so these galaxy formation physics are extremely nonlinear. That means it's difficult to solve with theory. You have to solve this with simulations. Okay? And one of the things that recently discovered, as you said, is that there are galaxies that appears to have no dark matter at all. Right? So it's just a galaxy that have only stars. Okay, very little invisible components. Okay, and people have suggested, oh, maybe this means that dark matter does not exist. Okay, and actually, some people claim maybe this is preference of the Mond-gravity model. Right? Maybe this means that gravity model should be modified, not the dark matter parts. But this is not new. Okay, it's always known that at the galaxy scales, because you have to do simulations from cosmology scale down to galaxy scales, simulation is difficult. Okay, and I have seen people claim that their new simulation can now produce an object that has very few dark matter but has stars. This is due to after you have two galaxies, okay, they then interact, sort of collide each other. Okay? A larger galaxy can take away all the dark matter, okay, and then the stars they just pass through, okay, and then a remaining object with no dark matter but with stars is formed. Right. Yeah. So the situation there, I think, is still non-conclusive. Okay, because there are groups that claim they can form it, but you need more multiple groups to verify that.
I see. That makes sense to me. Thank you.
But if a galaxy can gain all the dark, almost all the dark matter from another galaxy, can you use this to constrain the dark matter cross section?
Right. The interaction is not due to direct scattering. The mass loss mechanism is due to tidal stripping. They can do that because the dark matter is more loosely bounded. Okay, if you look at the rotation curve, dark matters are more extended than normal matter. Okay, so these parts are easier to get rid of using tidal interactions. Yeah, so it's purely gravity, so you cannot set any constraints.
Okay.
Yeah.
And Kenny, maybe I will have a follow-up question on the rotation curve. Thing that I always wonder is that, so currently, for example, in this picture that you show, we have measurement up to 35 kpc, but what will happen exactly if we further extend the profile to a much larger range, so that will the dark matter halo continue to go, or will it flatten, or will it have a sharp cut, or just what would happen?
Right, very good. So this thing will drop at about a typical galaxy scale is about 100 kpc. Yeah, so that's true. If eventually even the dark matter halo will cut off. It's just that the dark matter halo is on average more extended than the normal matter distribution. So if you do this, it will eventually cut off.
All right, thank you.
Yeah. So, but this part has not been seen, as far as I know, from direct observations. But we know that from N-body simulations.
Yeah, I'm actually exactly asking because actually when people do N-body simulation, they often places a cutoff in the dark matter halo, and that's why I was trying to think if this matches with the actual observation that we have.
Yeah, as far as I know, I don't think I have seen rotation curve that up to extremely large scale.
So you would say that you don't have enough data at this moment to tell whether that would be true or not?
I would say I don't know. I don't know whether we have data or not. Yeah, because
Okay.
I have maybe for Milky Way we may be able to do that with Gaia data.
Okay.
It would be actually something interesting to do.
Okay, thank you.
Any other questions?
Kind of a very tangent one. There's also one of the dark matter evidence is that the early universe model, but we also have Hubble crisis where the matter density doesn't, the model doesn't predict the expansion rate of the universe very well. Does this sort of relate to some unknowns in dark matter, or is that totally unrelated?
It's people have tried to use dark matter models to explain this. So to people who don't know, the Hubble discrepancy is saying that the Hubble expansion rate measured now using supernova versus the Hubble expansion rate inferred using early universe observation is discrepant. Okay, one I think is says 68, one says 74 or 72. So you notice that the discrepancy is actually relatively small. So in the grand scheme of lambda CDM, it does not really affect the whole picture by much. Okay, so it's a small effect, possibly caused by either the experiment was done wrong, or there's some small effect caused by new dark energy physics or dark matter physics. Okay. For example, some I think MC have tried to show that a dark matter that decay somewhat okay, in the middle of the age of the universe, not entirely decayed into radiation, but decayed into a slightly smaller, slightly lighter particle, but still remain non-relativistic, okay, could change this. Yeah. But to summarize, yeah, maybe it's telling us a hint that some interesting physics is happening in the dark matter sector. Maybe it is related to interesting physics in the dark energy sector. Right? We don't really know.
But in general, you would say that these two unknowns are not influencing each other. Like dark matter density is still that much. It doesn't change.
Yeah, it will not be changed by the, actually, this number is inferred using early universe, right? You're right. We don't have this particular number now, right? It may be possible that we are now at 23, right? Who knows?
Okay.
Yeah.
I have a follow-up question about the early universe. That can we use the idea from statistical mechanics? Like, for example, can we describe the early universe as like canonical ensemble, or is it like microcanonical, or is it even a pure state?
Yeah. So very good. Idea? Yeah. So very good. That's basically exactly how we describe the early universe. Each species is described either by a Fermi-Dirac or Bose-Einstein distribution. And depending on the situation, with non-zero chemical potentials. Does that answer your question?
Okay, basically.
Yeah.
So basically, why is it not like a pure state initially?
Well, it's depends on what you mean by pure state, because those are in thermal equilibrium, so they interact a lot. Right. So we can only use thermal macroscopic, right, thermodynamic descriptions for each species. Does that answer your question?
Yeah, I think so.
Yeah.